Welcome everyone. Thank you for joining the Ceratech webinar, Introduction to the Resilient Modeling Strategy. Michael, you can take it from here.
Hello, my name is Michael Hadley, and I am delighted to welcome you to this brief introduction to resilient modeling strategies. For information regarding hosting a full seminar at your location, please refer to the contact page at the end of this video. This class offers a compelling approach to 3D CAD modeling that fulfills the original promise of parametric design, the ability to edit and reuse models. Any designer using this strategy will significantly improve model stability while keeping design intent clear for anyone. As a side benefit, this method allows for a simple model quality verification, regardless of the complexity of the model. Note that this information is CAD neutral. Anyone who creates, manages, or uses solid models of any kind will benefit from attending. Every model is robust until someone tries to make an edit. The promise of parametric modeling was editability, but it has proven to be difficult to actually achieve. The first thing an editor has to do is relearn the feature tree and try to find all of the hidden parent-child relationships. Strategy is important because the change the editor wants to make now may not have been foreseen when the model was originally constructed. Changing values, relationships, or features can obscure or destroy the original design intent. Hitting the Finish button shows the change to the rest of the tree, and that is when the problems begin. How many times has it been faster for us to make a new model from scratch instead of trying to fix a tree full of failed features? In the interest of speed, many designers keep working on a model until it looks right and dimensions correctly in a drawing. This type of model appears robust until someone has to make a change. Then the true value of the model is revealed. Every model is robust until someone tries to make an edit. Some final thoughts before we begin discussing resilient modeling. It is very easy and fast to design parts when editability is not a criteria, but it only takes a small shift in strategy to create amazingly flexible models. Many designers don't like dumb solids because there is no feature tree. But they also don't like feature trees because they can be so fragile. As you will see, it is not difficult to make feature trees that are easily understood. The true costs of the way we model are hidden because everyone has the same problems with their models. Whether a widget company or a designer for hire, using resilient modeling strategies will benefit everyone. Resilient modeling strategy. Resilient modeling strategy is based on the idea that the feature tree can be designed to produce editable models, obvious models, and reusable models. Editable models are based on a predictable and readable feature sequence. If everyone in the company uses the same simple strategy, suddenly models are exchangeable and reusable. They can be started by one person and finished by another. Obvious models do not rely on intuition. Someone who has never met you and has no idea how you think should be able to inherit your models and make changes quickly and without any issues. If a model is editable, if a model is obvious, it is automatically reusable, and even better, it is likely to be reused. Before we begin discussing exactly how to use this strategy, let's take a moment to compare a traditionally constructed model with one using a resilient feature tree. The resulting models look identical, but only one is editable. While watching a replay of how the model using the feature tree on the left was constructed, imagine how you might approach this problem. This designer logically started with the basic shape for the first few features. Unfortunately, he immediately set a trap for later by adding rounds. Rounds consume prismatic edges and create derived boundaries that the CAD program shows as tangent lines. Note the complex intersections that get created with this feature. Deep in this CAD program, a lot of calculations are being performed to make this happen. Calculations that both slow rebuild or regeneration time and that are potential failure points if the derived tangent boundaries change. Note that the rib is 8 mm wide. The next feature, two 4 mm rounds, completely removes the defining surface. Here the designer uses a derived edge to define a new feature. And finally, the attachment holes are aligned to the center of the feature created by the protrusion number 6. Now let's look at the same model, created using the resilient modeling strategy. Even without knowing the exact specifications for this model, it is probably safe to assume that where it interacts with mating elements is pretty important. By creating the attachment hole locations in this way, we define the mating features and the height of the stabilizing arms at the same time. The body just ties the mounting holes together. Note that as we build these next features, any parent-child relationships are purposeful and functional. Now that the basic structure has been determined, let's add the detail features. These features will be children of the core features, but never of each other. Replace face is a powerful and often underutilized tool. Up to this point in the model, all features are prismatic. Every edge and every surface is fully defined and driven by either dimensions or constraints. In this model, we have chosen to make the rib rounds small enough that they do not fully consume the top surface, leaving a 0.001 mm wide flat, invisible to all but the CAD program, and many times more robust than the previous example. Two models that look the same, but that have a very different value to their owner. Let's dig a little deeper into resilient modeling. The resilient modeling tree is grouped and always starts with reference features. These can be layout, master sketches, schematics, datums, images, and the like. They are at the top of the tree so that any subsequent feature can see them and use them. The second group will contain the core features. This group is like a super base feature, made up of fully constrained and dimensioned prismatic elements with hard edges and clean surfaces. The third group contains the surface features, surfaces and curves that will be used later in the development of the model. The detail feature group adds functionality to the core, slots, holes, protrusions, cuts, and other details that flesh out the model. These features can have relationships with the reference group, the core group, or the surface group, but they cannot reference other members of the detail group. To assist with this, as we create features in the detail group, we suppress them so that they cannot accidentally be used as a reference or constraint for the next detail feature. If we find that a feature in the detail group needs to be referenced by another feature in the detail group, it needs to be moved to the core group. Once we are done, we unsuppress them all and move to the modify group. The modify group is where we perform patterns, mirrors, and drafts. This group may also contain what we call the final feature. This is a feature that might affect a number of the features in the detail and core groups. For example, a clearance cut through the entire part. This is always the last feature in the modify group. Finally, the sixth group is the quarantine group. The final cosmetic features that remove or consume material, leaving derived edges such as the tangent lines we discussed earlier. By placing them at the end of the tree, we have significantly reduced their ability to cause failures. We do still need to be careful when dimensioning these features in our drawings. In the next portion of this video, we will examine each group individually, highlighting the key elements of that group with a demonstration. This table details the content and strategies behind the 6 feature tree groups that we discussed earlier. By carefully arranging the order of your features and allowing only purposeful parent-child relationships, It is not difficult to build editable models. In fact, after making a few models in this way, it quickly becomes evident that this type of structure can actually speed up the design process. In the left column are the group names, followed by a description of each, and a list of the types of features normally found within each group. Note, for example, that extrude shows up in several groups. We have separated the groups by purpose and not by feature type. The links column is the most significant column. The relationship rule is simple. When you build a model in the correct order, if you can see the feature in the background, you can use it as a reference or a link. This is still true in the detail group, which is why after each detail is created, it gets suppressed. Detail features can only be related to core and reference elements, never to each other. Once all the details are complete, unsuppress all and move on to the modify and quarantine groups. For these last two groups, the single rule still applies. If you can see it, you can use it. At the very end of the tree, place the rounds, starting with the largest first. So far in our discussion of resilient modeling strategies, we have been focusing on the sequence of the tree. Another element of the strategy is creating models that are obvious. An obvious model is one that can be read and understood by simply looking at the feature tree. It does not require intuition, assumption, or interpretation. Intuition is defined as the ability to interpret something without the need for conscious reasoning. Unfortunately, how we interpret something is completely dependent on our own personal history and experience. An intuitive model is nothing more than a reflection of the author's bias towards what he or she thinks should be obvious. But my assumptions regarding what should be obvious are not going to be the same as yours. So anything that is left open to interpretation will be, and not necessarily in the way that was intended. What is truly ironic is that power users are often the worst culprits of creating intuitive solid models. The more experienced the modeler, the more likely they are to have developed an entire repertoire of shortcuts and workarounds. Part of the purpose of a solid model is to communicate design intent. There is one single step required to replace intuition with conscious reasoning in a model. Rename features as they are made. Labels like protrusion, sweep, and cut only describe the type of feature that has been created. By changing a feature's name to include function and quantity, suddenly the feature tree becomes a valuable resource for understanding without the need for interpretation. When the feature tree is made up of meaningful groups, labels, and quantities, everything necessary to understand the model is visible as soon as the model is opened. Unlike an intuitive model, an obvious model can be understood without having to step through the features. Take a look at the original tree for the connecting rod. If you wanted to modify the diameter of the hole in the end of the wrist pin hub, which feature would you go to? If you had just completed this model, you might remember where that feature is sitting in the tree. But 6 months from now, when tasked with an ECO, there is no way to know without stepping through the model or running a playback. Using the resilient modeling strategy, we already know that any hole is going to be in the detail group. And when we look there, not only can we immediately see which hole we want to modify, we can see its current size. The resilient modeling strategy process takes the guesswork out of creating and editing solid models. One of the comments we hear a lot is, "I don't have time to rename features." We get this from designers who think that their only job is to make models quickly. Who pays for this type of thinking? The CAD manager, the PDM administrator, the person who has to use the part in an assembly, and anyone else who might have to handle the model. Interestingly enough, there are also plenty of occasions when the original designer pays as well, by having to completely remake a model because a revision came through before the model was finished. So our question to you is this: do you expect models to be editable? If the answer is no, you may want to reconsider your answer. The smarter manufacturing and design companies are in the process of rethinking the value of their CAD inventory, and editable and reusable models are becoming a requirement. If the answer is yes, and you aren't getting editable models, we have a checklist that will be discussed shortly that should help. Consider this. If you have to make a single edit to a brittle model, you are no longer fast. If you are a designer for hire, this strategy will actually make you faster and allow you to easily reuse your legacy models from similar previous projects. If you work in the CAD department for a company, when your models are the only ones that can be quickly and easily edited and updated, you will get noticed in a very positive way. In most CAD departments, the people who stand out as stakeholders, the ones who care about revisions, ECOs, and data management, those are the ones who rise to the top. As we have already mentioned, models created using the resilient modeling strategies are easily reusable. Reusable models are the original promise of solid modeling. By using the resilient modeling strategy, a family of parts can easily be made. Simply create a master part and then create instances by renaming and changing a few values. When solid models are obvious and editable, an inventory of legacy parts suddenly becomes quite valuable. While beyond the scope of this video presentation, an additional benefit of the resilient modeling strategy is the ability to create an entire revision history within one model. For more information, please refer to the contact page at the end of the video. If parts are going to be reusable, it would be helpful if they were easy to find on your hard drive or server. Having an intelligent and consistent file naming convention helps tremendously with the reusability of your models. After years of study and dozens of books written on the subject, part numbering and naming really comes down to a few common sense rules. The first rule is, keep it simple. The more intelligence one tries to build into a part number, the more the variants and exceptions begin to accumulate until finally the whole system is so complicated that no one uses it. For fasteners and standard parts, again, keep it simple. A basic noun descriptor format is easy and flexible. The key to making this work is consistency. Now that you have seen an overview of the resilient modeling strategy, you are probably wondering how to make this work in your company. The first step is to develop a best practices manual. This has been attempted since the beginning of CAD modeling with marginal success. The main reason for failure has been that the manuals have been too long, too complicated, and too focused on minutiae. Only 3 things are required to create a successful best practices manual: a list of the minimum requirements necessary to create editable, obvious, and reusable models, a quick and simple way of communicating those requirements, and a verification checklist. These days, the only useful purpose of a best practices manual is to create a pathway to valuable solid models, to clarify the guidelines so that everyone in the company can make equally robust designs. The key to the content of the manual is simply to focus on information that will lead to editable and obvious models. For drawings, refer everyone to the ASME standards. Instead of some huge notebook that gathers dust on a shelf somewhere, make the best practices manual into a set of indexed training slides, a presentation that can be viewed in its entirety, or a specific point referred to whenever needed. Examples like the ones we have shown here should be available for every major concept, and, most importantly, the presentation should be kept current as software updates and feature creation capabilities improve and change. The most important aspect of the Best Practices Manual is a verification checklist. This is a tool that every designer can use to verify their own work before a design review, and every manager can use to quickly perform a quality audit. Without a checklist, a Best Practices Manual is just another specification that no one reads. A checklist should be just that, a set of bullets listing items that either are or are not present in the model. If the purpose of a Best Practices Manual is to promote the creation of editable and obvious models, a simple checklist can actually verify compliance. Below is a brief stylized checklist that would verify that the basic guidelines of resilient modeling have been followed. Even this short list would be very handy for a designer to check his or her own work, or for a design review team to use to quickly review the value of a submitted model. Thank you for your time. We hope that you found the information in this short presentation valuable. If you would like a deeper look into any of the concepts presented here, or would like to attend a complete presentation of resilient modeling strategies, please let us know through any of the contact points below.
Thank you, Michael. Due to the limited time we have for these events, we can only show you certain features. Therefore, if you have additional questions, please feel free to contact Dick Gebhard. This concludes our meeting today. Please take a minute to fill out the survey that will pop up on your screen as you leave the webinar. We appreciate your opinions and do use your feedback to improve future webinars. Thank you so much for joining us and have a wonderful day.